सभी को नमस्कार। क्यूमेट 2026 के इस उद्घाटन समारोह में आप सभी का हार्दिक स्वागत। On behalf of the organizing team, led by my colleague Professor Satyavrat Patnaik, I extend my very warm welcome to all of you to this 8th annual conference on quantum condensed matter, that is QMAT 2026. Since the very first QMAT conference organized by Gautam Sheet, Krishnendu Sen Gupta, Rajdeep Sen Sarma and Pratap Rai Chaudhary in July 2018 at IISA Mohali, this event has actually evolved into a very regular and vibrant event for community gathering, where people exchange ideas and forge collaborations. About a year ago, or maybe a little more than that, Satyavrat had gone to IIT Guwahati to attend the previous edition of QMAT. And from there he called me, "Sir Brijesh, I would like QMAT to come to Delhi." And I told him, well, please go ahead and lead the way. And we will support in whatever capacities we have to make that happen. So indeed, he led the way, and here we are today to inaugurate this big event of, I think, more than or nearly 600 participants. And it is thanks to the community, which showed great enthusiasm and support for this meeting. And also, we are very grateful to the partner institutions, IIT Delhi, NPL, and Bennett University, for making this QMAT 2026 happen here in JNU. So welcome you all. Before I sort of go ahead with proceedings further, the main highlight of this evening is, of course, an inaugural speech by Professor Ganapathy Bhaskaran from Math Science. Before we do that, as always, we would like to start with Swasti Vachan. So I would invite you and other students to please come on stage और स्वस्ति वाचन से इस समारोह का शुरुआत करें। आइए।
ॐ उद्वयन्तमसस्परे स्वः पश्यन्त उत्तरं देवं देवत्रा सूर्यम् अगन्मज्योतिरुत्तमम्। ॐ वेदमनुच्याचार्योऽन्ते वासिनमनुषास्ते सत्यं वद धर्मं चर स्वाध्यायान् मा प्रमदः आचार्याय प्रियं धनमाहृत्य प्रजातन्तुं मा व्यवच्छेत्सीः सत्यान्न प्रमदितव्यं धर्मान्न प्रमदितव्यं कुशलान्न प्रमदितव्यं भूत्यै न प्रमदितव्यं स्वाध्याय प्रवचनाभ्यां न प्रमदितव्यं देवपितृकार्याभ्यां न प्रमदितव्यं मातृदेवो भव पितृदेवो भव आचार्यदेवो भव अतिथिदेवो भव यान्यनवद्यानि कर्माणि तानि सेवितव्यानि नो इतराणि यान्यस्माकं सुचरितानि तानि त्वयोपास्यानि नो इतराणि एष आदेशः एष उपदेशः एतद् अनुशासनम्। अथ अग्निसूक्तम् ॐ अग्निमीडे पुरोहितं यज्ञस्य देवमृत्विजम् होतारं रत्नधातमम् अग्निः पूर्वेभिरीर्षिभिरीड्यो नूतनैरुता स देवाङ्गेह वक्षति अग्निनारैमश्नवत्पोषमेव दिवे दिवे यशसं वीरवत्तमम् अग्नेयै यज्ञमध्वरं विश्वतः परिभूरसि स इद्देवेषु गच्छति अग्निर्होता कविक्रतुः सत्यश्चित्रश्रवस्तमः देवो देवेभिरागमत यदङ्गदाशुषे त्वमग्ने भद्रं करिष्यसि तवेत्तत् सत्यमङ्गिरः उपत्वाग्ने दिवे दिवे दोषावस्तर्धिया वयम् नमो भरन्त एमसि राजन्तमध्वराणां गोपामृतस्य दिदिविं वर्धमानं स्वेदमे स नः पितेव सूनवेग्ने सूपायनो भव स च स्वानस्वस्तये इति शान्तिः शान्तिः शान्तिः।
इस सुंदर प्रस्तुति के लिए बहुत बहुत धन्यवाद। आप कार्यक्रम को आगे बढ़ाते हैं। So the program is very simple. Before we go to Professor Bhaskaran's inaugural talk, I would like a few colleagues to make opening remarks. First, I will invite Professor Pritam Mukhopadhyay, Dean of SPS, and my dear colleague, Professor Mukhopadhyay.
Thank you, Professor Brijesh Kumar. A very good evening, distinguished guests, esteemed speakers, colleagues, and dear participating students. On behalf of the School of Physical Sciences, it's my privilege and honor to welcome you to the inaugural ceremony of QMAT 2026. I am absolutely thrilled to see such a vibrant gathering of minds. Your presence will definitely elevate this conference. To all the participants who have traveled from far, welcome to our beautiful JNU campus. See the blooming nature in this rainy season to come. For the QMAT, 224 eminent speakers, more than 350 PhD and postdoctoral researchers, an event of this magnitude does not happen by chance. It's the result of vision and relentless hard work. I want to extend my heartfelt appreciation to the organizing committee, most notably Professor Satyabrata Patnaik, the convener, and his dedicated team from SPS JNU, IIT Delhi, NPL New Delhi, and Bennett Delhi, who have worked tirelessly over the past few months to ensure this conference is both academically rewarding and deeply memorable. QMAT has grown into a premier benchmark for scientific discourse, and this year QMAT 2026 serves as a vital bridge connecting fundamental physics with the disruptive technologies for tomorrow. As the Dean of SPS, School of Physical Sciences, I am extremely proud to introduce to you about the School of Physical Sciences. Since its inception in 1986, the founder member is there, Professor Shushantu Dattagupta is there in the audience. SPS has over the years become one of the leading departments of India in research and teaching in physics, chemistry, and mathematics, as well as the interdisciplinary areas bordering them. Our rigorous academic curriculum and diverse postgraduate programs in Masters in Physics, Chemistry, and Mathematics and PhD in Physics, Chemistry, and Mathematics are specially designed to foster deep analytical thinking. Our core research areas span from condensed matter physics, theoretical physics, synthesis of complex chemical systems, advanced material science, ultrafast spectroscopy and dynamics, single molecule spectroscopy, to the algebraic and analytical number theory, arithmetic geometry, dynamical systems, probability theory, and many, many more. Our faculty members are regularly recognized with prestigious national and international fellowships, grants, driving high-impact research published in top-tier global journals. Equally inspiring our students who consistently secure premier research placements and push the boundaries of innovation. Our students have become faculty in ICERs, IITs, JNCSR, ISC Bangalore, and so on. They are also serving reputed industrial houses, global pharmaceutical companies, and few of them have become well-renowned entrepreneurs. SPS stands today as a beacon of academic excellence because of their brilliance. However, the greatest scientific breakthroughs are rarely achieved in isolation. Progress thrives on collaboration and partnership. Looking out at the incredible expertise in this room, I see an unparalleled opportunity, and I invite and urge the experts here to collaborate deeply with SPS. Our state-of-the-art laboratories are open, our faculty is driven, and our students are exceptionally talented. Let us combine our strengths to co-author the next chapter of scientific innovation, launch research initiatives, and try to solve the complex academic challenges of our time. In closing remarks, I want to express my gratitude to the entire SPS staff, the colleagues, the student volunteers, and every individual working behind the scenes. Your quiet dedication is the engine that makes today as possible. To our participants, I wish you next 4 days of stimulating debates, transformative insights, and new friendships. May your time at QMAT 2026 be intellectually fulfilling and deeply memorable. Thank you very much, and I wish the conference every success.
Thank you, Preetham. Next, I invite Professor Rajendra Singh from IIT Delhi. IIT Delhi is a partner institute in this event, and I think you could just, up to you. See, the basic idea is that it's not just JNU, but JNU, IIT, NPL, and Bennett, all four are partner in this. So you are representing IIT Delhi in some way, but you can just speak for 2 minutes.
Okay, maybe 2
minutes.
Okay.
Nothing much is expected.
Yeah. Okay. Thank you. So myself, Rajendra Singh, I am from the Department of Physics, IIT Delhi. But the context in which I am, let us say, right now speaking is, I am also currently the project director of one of the thematic hubs under National Quantum Mission, which is Quantum Materials and Devices Hub. And it has been established 1.5 years back at IIT Delhi. And as you know, under the National Quantum Mission, so there are 4 hubs. One of the hubs is let us say in quantum computing, which is at IIT ISC Bangalore. IIT Bombay is quantum sensing and metrology, and the third one is quantum communication, which is at IIT Madras. And this whole National Quantum Mission is working in a hub, spoke and spike model. So we have actually, let us say, various technology groups under each of these hubs. So I will just, let us say, talk only about our technology groups. So there are 14 technology groups which are generating some technologies related to the quantum mission, actually, whether it is in communication domain, computing, or let us say sensing and metrology. And under materials and devices, currently we have 3 technology groups. One of them is on 3-5 compound semiconductor based heterostructures, quantum heterostructures. And second one is on 2D quantum materials, which is, like, let us say, the lead PI is at IIT Bombay. And then the third one is on silicon nitride thin film based integrated quantum photonics, which is based at IIT Kharagpur. And there are multiple, like, let us say, MPIs, member PIs associated with each of these, like, let us say, technology groups. And there are 3 or 4, like, let us say, emphasis, the points where we emphasis on, in, like, let us say, one of them is technology generation, which is done through the technology groups. Second thing is the HRD. like let's say creating skilled manpower workshops. So this is like let's say one of the workshop which is happening here, being also supported partially by the QMD hub. So this is also one of our mandate. The third one is the startup and industry and entrepreneurship. So we have actually dedicated funds. Many of like let's say those who you don't know, this is also very important point, that we have dedicated funds for the startups. So if you have some idea in any quantum area where it is like let's say in our hub it is for quantum materials and devices. So if you have idea, then like let's say up to 5 CR can be supported for the startup. So the entire like let's say 5 CR is there. It can go even beyond that also, but then it goes like let's say to the DST for final approval. And the fourth one is international cooperation, and like let's say we have exchange visits of the international experts also. Very briefly, I am telling you, we have our website also, qmdhub.co.in. We have our CEO and complete team is there. Mostly they are looking into all these aspects. We are actually like let us say more working into the technology generation and also like let's say doing research. Right now the more emphasis is on the technology generation currently, but we don't know in the future, like let's say there will be more, some emphasis can also come back on the basic sciences. This is what we are hoping for. So with that, I think very briefly I just wanted to tell you about our QMD hub activities. Thank you.
Thank you, Professor. Thank you very much. So next I invite Professor Lata from she is the dean of School of Applied Science and Engineering in Bennett University. Please.
A very good evening to all of you, and dear distinguished guests, leading researchers, students, delegates, and participants of QMAT 2026. On behalf of Bennett University, I welcome you all to this grand mega gathering of quantum people here. And the Bennett University, with its rich 185-year-old legacy of the Times Group, is one of the leading multidisciplinary institute which is committed to academic excellence, research, innovation, and entrepreneurship. And I'm very happy to inform you all that we are celebrating the 10th anniversary of the establishment of Bennett University this year. And since the beginning of the Bennett University, the Department of Physics has been very active and very dynamic in one of the applied sciences branch. And we have faculty who are research driven and who have the research areas spanning from quantum to condensed physics. I'm not from the physics background, I'm from the biotechnology background. And I'm told that there are physicists who are working in the area of biophysics, statistical physics, and all other leading areas of physics. And the faculty is also awarded with external grants, and we are committed to a student-centric environment, research-centric environment at Bennett University. And I'm very happy that we are partnering with leading institutes, the IIT Delhi, JNU, NPL, and we, along with the Department of Physics at Bennett University, is organizing this event. And I thank Professor Patnaik and their team to be allowing us to be part of this mega event. And I congratulate Department of Physics at Bennett University, particularly the head of the department, Dr. Ayan Khan, who is here. And I'm sure this conference is going to be a very stimulating and enriching experience to all of you. And I'm sure the next few days will be an enriching experience to you all. Thank you very much, and thank you for your attention.
Thank you, Professor Lata, for your nice words. Next, we have, at least in my list, 2 more names, but I don't see Arindam Ghosh here. So he's still flying, I guess. Never mind. So let me invite Professor Pratap Rai Chaudhary to come and speak very briefly about his views on QMAT. In fact, as I already mentioned, he is one of the founding organizers of this series of events, and has been ever enthusiastic about it. So, Pratap.
Okay, good evening, everybody. I'm sure that you are all waiting for Professor Bhaskaran's talk, so I'll be very brief. This seminar, this conference series was started in 2018, as you have heard, by some of us, mainly Rajdeep, Gautam, Krishnendu, and myself. The aim was to have a meeting which is roughly sort of inspired by APS March meeting, which will be a community meeting where the entire community can meet every year. And the idea is to have as little barrier as possible for participation. So we wanted to have the entire community meet. However, there are logistical constraints that prevented us from achieving really that in previous years. In particular, we had been so far following a policy that no one would give any invited talk in subsequent years. It can at most be in alternate years. But that also meant that eventually the community was split into the odd year community and the even year community, because the senior people typically came when they had a talk. I'm very happy that this year, this being in Delhi, and thanks to the effort of Satyabrata and his team, we have been able to transform it for the first time into a true community meeting. I don't think that their team denied anyone who expressed an interest to participate, and that is why we have 5 parallel sessions. There is also, of course, another aspect. We rotate this conference in various places, and in some of the places, like for example, last year it was in IIT Guwahati, there even if we wanted, we could not go beyond a size because there are no hotels around where people can find accommodation, transport is not easy, and it has been always our policy to keep all these frills to a minimum. So we expect the participants to arrange their own transport. We help in accommodation, but we very strongly also encourage them to find their own if it is available. And in Delhi, all these things are more or less available. So that also allowed us to expand the size this year. Now with this, as you have heard, we have around 600 participants, and I think the next few days will be very exciting for all of us. And welcome again. Thank you.
Thank you, Pratap. Thank you very much. So now we come to the main part of this session, which is the inaugural talk. Professor Bhaskaran is too well known. He doesn't need to be introduced, but the occasion demands that I still introduce him. Some of us know him for a long time and rather closely, but a lot of, especially the new members of the community, I think it's important that I formally introduce him before I invite him to deliver his inaugural speech. So let me very quickly tell you about Professor Bhaskaran. He is a very highly acclaimed and widely respected theoretical condensed matter physicist. In fact, I like to sort of put it like this. He's truly made in India physicist, celebrated worldwide. And the reason why I'm highlighting this point is that people who grow up in various Indian settings, not necessarily full of opportunities or directly in connect with the rest of the world, and they still aspire to be making big in the world of physics. Here is an example. He is a fully made in India physicist, celebrated by the world. He did his basic education in Madurai, and his PhD was done in ISC Bangalore under the supervision of Professor K.P. Sinha and N. Kumar, very distinguished physicist. After his PhD, he was at ICTP. In fact, at ICTP, International Center for Theoretical Physics. It's a UNESCO center based in Trieste, Italy. He has had a very long association, and in fact, after that, he spent most of his time as an independent academic at Math Science, the Institute of Mathematical Sciences in Chennai. He was a professor there. Some years ago, he superannuated, but he still holds a emeritus position there. He is also a distinguished professor at IIT Madras, and he also holds a distinguished visiting research chair at the Perimeter Institute in Ontario, Canada. As I said, he's a remarkable physicist, and of course, there are many awards which have come his way. He was, for instance, the first ICTP prize winner. So ICTP instituted a prize in, I think, 1982 or 83, but he got it in 83. So that was the first time ICTP gave out prizes for young scientists from developing countries. He also received Shanti Swarup Bhatnagar Award in 1990. He is fellow of Indian Academy of Sciences, Bangalore, and the Indian National Science Academy in Delhi, and he's also a fellow of the World Academy of Sciences. Some of his most creative contributions to physics, for which he is known, are, for instance, the most famous one is the RVB theory, the resonating valence bond theory. Students from basic chemistry must have heard of Linus Pauling's resonating valence. And in 87, in collaboration with Professor Phil Anderson, whose photo we saw just a while ago, they developed a very beautiful theory for understanding the high temperature superconductivity in cuprates. It's a class of ceramic materials which exhibit superconductivity at actually very, very high temperatures compared to, I mean, not at room temperatures, but compared to the conventional superconductors. So that was his one of the most remarkable pieces of research. In the same context of studying and understanding strongly correlated electronic problems, he also, for the first time, sort of developed the idea of emergent gauge fields. In fact, later on, Kitaev's model, some of you would know or learn about it during the conference, realizes those gauge fields as exact constructions. He also, as I said, he also worked on Kitaev model, in fact. He and his collaborators studied exact spin dynamics of Kitaev model. It's a very beautiful piece of work. In fact, there is one place we also had a friendly competition. I was a PhD student, and one of my paper appeared just 7 days after Professor Bhaskaran's paper. And these two papers are pioneering papers in triangular lattice mount insulators and superconducting systems. So there was a class of materials which have cobalt oxide layers, and they exhibit superconductivity. And Professor Bhaskaran was the first one to sort of give basic microscopic understanding of this class of materials. And just to conclude this little introduction, Professor Bhaskaran represents the best of quantum condensed matter physics. And I am deliberately not putting Indian condensed matter physics, but the condensed matter physics as condensed matter physics anywhere. So he represents the best of quantum condensed matter physics. And we are extremely delighted and grateful that he is here. And I think it is just about time that I stop talking and Professor Bhaskaran starts speaking. So I invite you to deliver your inaugural speech on blooming garden of quantum matter. Professor Bhaskaran.
Thank you, Brijesh, for a very kind introduction, glowing introduction. I do not know if I deserve that. I thank Satyabrata and company for inviting to this wonderful garden. You know, I view you people as a quantum garden of blooming garden of quantum matter, where the future of quantum garden physics, quantum matter physics. So I'm very happy to be with you. And next 45 minutes or so, I will be telling some stories. So having given this title, then I thought I will do a random walk in the blooming garden of quantum, because that's the only thing I can tell stories and exchange some jokes and views and so on. That's what I plan to do. Now, I dedicate this talk to three people whom all you know. One is Professor Rajaraman, who was a key founder of this department, School of Physics, and so on, played a very important role. And then Vikram Soni, some of young people may not know him, was a nuclear theorist, outstanding, I will tell about him, and Tony Leggett, a Nobel laureate. So I met all of them in Delhi, and they are friends of Delhi and so on. So they played important roles in my career path. I will try to tell it briefly in the beginning. Satyabrata pointed out that I should do some physics, but I tried to avoid doing too much physics, because in the evening at this time, after a lot of coffee and so on, physics can be bad, too much technical physics. So let me tell some stories. So there is a YouTube lecture in Math Science, the title Science Out of the Box. I talk about various friends of mine whom I know personally, who are outstanding scientists, but in addition to they do wonderful other things. So that's the title of my, so you can all look at it. So Sony is an amazing guy. He met me in 1976, just when I became a postdoc at IISc Bangalore after submitting my thesis. He came to see his friend Haridas. He came there as a PhD student from University of California, Santa Barbara. So we became good friends. And then we started talking about nature and many other things. So he joined. Then he went to Sussex and did a postdoc with Tony Leggett on beautiful work on what is called Sphaleron or Sonion and so on. And then he came back to Madras. He had got good job offers from other places, but he chose to come to Department of Theoretical Physics in University of Madras, and he was there for 3 years. So we became collaborators and so on. So we started, he did his PhD on pion condensation in nuclei, in nuclear matter. And then with Tony Leggett, he started working on topological solitons and so on. Then he started working on magnetons, neutron stars. Then on the way, see, as a matter of principle, I open my cell phone only 3 times a day, at 9 in the morning, 1 o'clock in the afternoon, and 6 in the evening. Other times my cell phone is meditating. So we started thinking about nature, and we are all, this campus is in a beautiful forest campus, right? It's called part of Aravalli campus. And many people do not know Delhi is full of these ridges spreading all over. And Vikram Soni and his friends are responsible for what it is in the status now. Because there was a lot of encroachment by army and multinationals and so on. So they worked hard and struggled hard and really saved it. And then in the process, we do a beautiful book called Naturally and so on. And Rajaraman, as you all know, I don't need to talk about Rajaraman here to younger people here in the, but to younger people, the amazing nuclear theorist who did his studies at Delhi University, and he became a student of Hans Bethe, did beautiful work on triple correlations in nucleons and nuclear matter and so on. So wonderful teacher. Now I have to acknowledge that I was fortunate to be there at Indian Sub-Science Bangalore when Rajaraman joined Center for Theoretical Sciences as a professor, and he gave us a course on quantum field theory. So I was a very shy student because I was afraid of del mu and del epsilon mu nu lambda and so on. Field theory was scary to me. He told me, Bhaskaran, don't worry about it. And continue to use your del cross B and vector product and so on, dot product, cross product. Don't worry about epsilon mu. Also, he told me, I ensure that gauge theories and all these high energy physics theories are collection of interacting harmonic oscillators. You know a harmonic oscillator well is. I told him I know it well. Then you know quantum field theory. That's the confidence he gave me. And then he encouraged me to learn gauge theory and so on, which later helped in my career. So he was an amazing teacher. And then he's a collaborator of famous Bell, inequality Bell, Shankar Ghosh, who is in IIT Delhi, and Shivaji Sondi, who solid. Then the amazing thing is, he will also, I mentioned about him briefly in my talk, so doing science out of the box, but since there was no time, I didn't describe his work in detail. Even as he was doing his science, he was fascinated by the world at large. There were a lot of nuclear threats and so on. So he spent a lot of time as a peaceful scientist, messenger of peace. So for example, he tried to talk to Pakistanis and Indians and tried to calm them down, don't proliferate nuclear weapons. And then later he became a very internationally well-known figure in the nuclear scenario arena. So I will not talk about it. So from nuclear physics, nuclear disarmament, and he's an amazing person, worth following. Tony Leggett, as you know, he passed away again some 6 months ago or so. He's Nobel Prize in Physics. He's an amazing person, very quiet and calm person. So he and Sony became good friends because he was a postdoc. Sony was his postdoc. He used to visit Delhi regularly. So I will show some photographs. And he has this famous Caldera-Leggett theory of dissipation in quantum systems, Leggett-Corgan inequality, superfluid helium-3, and so on. And he helped indirectly development of science in the third world. That's what his role is. You look at it, he was like a man in black. That is, he helped people without them knowing that. So there are many instances I can tell about him. He's a great man. So since I knew all the three, so this is a picture that was taken in Vikram's house when Vikram Soni lived in Vasant Vihar. We were discussing something seriously. In fact, I am there in that picture on the other side. I cut it off. Rajaraman is there. Then Vikram is a very effective chap. One day we were talking about solitons and polyacetylene and so on. Then I talked about thermal effect on the fractional charge carried by polyacetylene, like domain walls. So next day Sony came with I gave a heuristic argument in terms of using Boltzmann factor and so on. Vikram came with a beautiful diagrammatic method using Goldstone-Wilczek diagram, and he did the same thing in a beautiful way. So we have a PRL. That's one of the first work that we did. Then he laid foundation. He became the founder of this PS. I will talk about it later. Then, before I forget, so we are talking about models and so on. There are role models, we have worth following in Indians. In the recent context, we have Majumdar Ghosh model. It's a lonely model that is there, that was written down. I will tell about it later. And then, it suddenly got some excitement and lots of physics came. And anyway, I will not talk in detail. Later I can talk to people privately. One of the inspiring models. Then Jainendra Jain's composite fermion model. In fact, Jainendra will be here, I think, in this conference. He recently got Wolf Prize. So, Jainendra Jain's composite fermion model, and then Haldane Shastri models. I think Brijesh was a student of Sriram Shastri. Wonderful models. So I think they are role models to follow. Then, of course, Subir Sachdev and A. and Kitev. See, it was wonderful that when we were struggling with RBB theory to study triangular lattice and regular lattices and so on, Sachdev and A. came and wrote down a beautiful, exactly solvable model, which was not respected by the community that much at that time. It was lying there idle till Kitev noticed a beautiful exemplification of ADS-CFT correspondence, well known, very popular these days. So it became all of a sudden a famous model. In fact, it's the most cited model in the recent time. 3 Nobel laureates have written papers, including David Gross and others. Ed Witten has written 3 papers and so on. Then, I do not know how many of you know, there is Deshjit Sagdi, who is not far from here. He is a model to follow in the sense, I met him for the first time in ICTP when he returned from the US. as a postdoctoral fellow, doing cosmology. Was doing wonderful cosmology work. He joined IIT Kanpur, was doing cosmology. At some point, he decided to give up everything and start making instruments for Indian science, and also doing the science based on his own instruments. So, if you want an STM machine at room temperature that works at room temperature, you can ask him. He will give it at 1/10 of the cost that is available. So, he is a model. I want to just embrace him. He's a model for Indian science. I think he will have a Devship will have a poster in the what is it? That stall. His company's name is what is it? Quasar. Yeah. Anyway, please talk to him. Now, this Aravalli range in Rajasthan. If you look at the map of North India, you see this Thar desert. Adjoining that is Rajasthan. At the end of Rajasthan, this is Aravalli mountain, very special mountain. It's even older than Himalayas, geologically speaking. And this mountain extends up to Delhi. Delhi is at the tip. What is special about this mountain is that if you go to the ridge area, you see these peacocks. I have seen them, squirrels and foxes and so on, beautiful creatures, flowers. Now, what did Sony do? He and Devship and other friends worked very hard to save them. By the way, I think this is one of the pictures I took last time when I visited JNU. The beautiful peacocks. It's also a beautiful it's part of the Aravalli forest. There is a nascent forest all over the campus. It's a large campus, somewhat like IIT Madras, but IIT Madras is much denser and there are nothing like, it's not like dry thing and so on. Sony also had this idea of floodplains. I will not go into the details. Then he had this idea of natural cities. Anyway, okay. So, what is great about Sony is that he was a condensed theorist, nuclear physics. He worked on collision of black holes and so on. But at the same time, he started this foundation called Public Interest in Science. M.S. Swaminathan was so excited, he volunteered to become one of the founding members. So he worked very hard in it. Tony Leggett, Sony and Rajendra Singh, the waterman of India, Arvind Virmani and others. So I encourage you to look at this website, young people. Because beyond science, you can do many, many things. For example, Rajaraman, today I came across this beautiful article in Bulletin of Nuclear, I don't remember the full name, Bulletin related nuclear thing. Described very well Rajaraman's involvement, how he got involved in this. This guy's name is Ramana, I know him, he was at Princeton. And then Ramana, and then I forget his name. Yeah, I know most of the people. And it's a very nice place where Rajaraman's work beyond physics is explained in a very beautiful way. This is what I wanted to tell. Okay, role models. See, whenever I talk about physics, I tell them importance of mathematics. It is Wigner who always emphasized the importance of mathematics in science because he used it very well, very effectively. And he also wrote a beautiful paper called Unusual Effectiveness of Mathematics in Science. I encourage you, if you do a Google search, you will get it. It's a beautiful short article worth reading. I encourage people to look at it. Also, Wigner had the following thing. It's very relevant in these days. Many years ago, there was handheld calculator, hand machine calculator. So somebody calculated something very beautifully, got very good numbers, and went and presented Wigner the result. Wigner said the results are very impressive. It's very clear that the machine understands what's going on. Do you understand it? That was Wigner's question. So the same question can be asked now, because we use AI and numerical methods and so on, but do we understand what's going on? It's a very important question, but there are people thinking about it. So now when I'm talking about quantum matter and so on, any science, observations and experiments are key things, and technology drives this. So there is a modeling phenomena, concepts, notions, laws, hypotheses, dogmas are brought in. Then so it's the interplay of all these things which is a basic science. Very, very important. It's important to realize this, because then once you realize this, you won't be afraid of any one of these. For example, you will not be afraid of mathematics if you are a theoretical, if you are an experimental physicist, or you will not, because if you look at the way things have happened, great work are done by very beautiful experimental physicists. Theoretical insights are given. Okay, matter is quantum. Let me take a piece of rust, Fe2O3. Rust is mostly this hematite. In Chennai we have plenty of rust. Because of sea breeze, we have this oxidation of even I'm afraid that I may become rusty someday. So it's so rusty. And the rust is a beautiful Mott insulator. There is a lot of Mott physics there, antiferromagnetism, ferromagnetism. A grain of sand, if you take quartz or whatever it is, there's quantum physics there. And a drop of water and a paisa coin. If you take a copper coin, it's supposed to be a Fermi C. Copper is one of the first things to be understood in terms of polyparamagnetism and Fermi C notions by Sommerfeld and others. And in fact, it has a very important role in the context of India. We know that Chandrasekhar became famous because of his Chandrasekhar's mass limit and so on. The story is the following. C.V. Raman was at Calcutta. He has invited Sommerfeld to visit Calcutta and gives about 10 lectures on quantum mechanics. So in those days, the route to Calcutta is via Chennai. That you come by land in Chennai airport and then take a train and go to Calcutta. So he landed in Chennai port. It's what Presidency College was. They knew about the arrival of Sommerfeld, so they welcomed him and asked him to give a talk about what's going on in quantum physics. So he told about the notion of Pauli principle, how it has implications, beautiful implications in the case of metals like copper, simple metals, notion of Fermi C and Pauli paramagnetism and so on. Young Chandrasekhar was sitting in the audience as an undergraduate student and listening to the talk by Sommerfeld. And later he asked some questions. Then it was in his mind when he developed this theory of gravitational collapse of self-gravitating matter and how Pauli principle works against gravitation, with the balances of Chandrasekhar's mass limit. Amazing thing. He applied it to relativistic context. So I always tell students, please attend talks. Whenever somebody is passing by, please attend talks. Don't ignore talks. See, I'm telling my personal experience because attending talks are extremely useful and very valuable in your career. Normally these days people tend to avoid attending talks because they will rather look at their cell phone rather than attending the talk. There are more things in cell phone than somebody is looking at the cell phone. Sorry, I'm not telling you. So, in fact, I will tell you one incident. Once I was traveling from Chennai to Mahabalipuram, about 30 miles. So I got into the bus to meet a friend of mine that many of you know him. His name is a Russian, Paul Wigman. He was visiting Mahabalipuram, so I was going to see him. So I got into the bus was crowded. I looked for a place, nobody was looking at me, everybody was looking at the cell phone. There was nobody, there was some place, nobody could, even they didn't move an inch. Only the driver looked at me and smiled and gave me a ticket. And then till I landed in Mahabalipuram, nobody looked at me. So they were all wedded to the cell phone. So that's the way things are now. So please remember there is a world around us, world of people like me. Okay, so what did these guys do? Newton, Maxwell. So what did they do? They looked at experimental results, series of experimental results, a body of experimental results, and they contemplated and thought about it. Newton came up with Newton's law, Maxwell, Faraday, Gauss, all these people. And what did they do? They did develop. If you look at Einstein's theory, is fantastic. Before quantum mechanics was completely born, Einstein gave this idea of. He was worried by the phenomenology, namely, the specific heat of a solid at low temperature doesn't vanish in the theory. Experimentally, it vanishes. So that's against Dulong-Petit's law. So Einstein worried about it. He said, I could explain it if I think that each atom is trapped by its neighbors, it's in a harmonic well. And he became the first solid-state theorist to do this Einstein theory. And it explained qualitatively what was going on correctly, namely the vanishing specific heat at low temperature. Everything else, then Debye came and corrected it, there was acoustic modes and so on. So models are extremely important. This is a very simple model before quantum mechanics was matured. Then similarly, electron is specific heat. So most of them analyze and contemplate and experiment, use their imagination to build a simple but non-trivial method. It's a very important message is, if possible, build a model of your own. For example, if you take rust, rust is, Fe2O3, sometimes water molecules are stuck to it. And it was Zener, Anderson, Hasegawa looked at rust and hematite. They essentially brought the notion of motor insulator effectively. About gave a model, beautiful model, grain of sand. So it tells us geological history. In addition, they're part of amorphous and glassy material. There's a physics in glass, lots of universality physics, and later it becomes spin glass and so on. Drop of water, hydrogen, this amazing thing. Even now, we don't understand water that well. If you talk to Michele Parinello and other friends who are working on water, they say we don't understand water. Even though there is hydrogen bond, there are classical potentials and so on. But actually, we do not know quantitative also. There are probably many quantum effects which are subtly there even at room temperature. So water is a very mysterious system even now, particularly in biological and small environment. Like the water chains are formed in biological proteins and they are sucked in and so on out. So also recently there is a beautiful discovery. I'm looking at this helix, like a double helix. It's a very few years old. You take a double helix, then people did not know that there are nucleic acids which form this double helix. What they also found is there is a water chain which is a water helix that is winding around it. So it's a new research discovery thanks to cryo-electron microscope, because they can look at even protons and hydrogen atoms. So there is a new discovery that in addition to what you see in a helix, there are water chains which are exactly running around. What do they do? I have some vague ideas about it, but beautiful things are happening with water. Now quantum matter, if you are talking about quantum materials and so on, gas, liquid, solid, magnet, sponge, so many materials. Okay. Now when you look at this, it's not that these are all phenomena. The idea of theorist is to abstract and bring some concepts. There are key players in it, wonderful things have been done. Just for example, if you take, what did Sommerfeld do? Sommerfeld was familiar with the Pauli's exclusion principle. He said, if I have to explain linear specific heat at low temperature and Pauli paramagnetism and so on, then I have to form a Fermi sea in momentum space. That's a very key notion which has been dominating our physics, metal physics for a long time. There are of course beautiful departures from that. Similarly, BCA superconductor, free Bose gas. It was a great resonance between Bose and Einstein. Einstein criticizes Bose criticizes Einstein's theory of Bose statistics. He says there is a logical inconsistency. If you assume indistinguishability, everything will work out well. And so he writes a famous letter to Einstein. Einstein was so impressed by it, he goes beyond and he puts finite chemical potential and he gets this Bose-Einstein condensation. It's a beautiful respect for each other and then think. So that became a free Bose gas, basis of Bose condensation, like in lasers and so on. It will be strongly correlated to Mott insulator, Kondo insulators, non-Fermi liquid, Lettinger liquids, tomographic and so on. Many things are happening. Now what is happening is, after the advent of quantum Hall effect and composite fermion theory and so on, new things have happened enormously. There is a beautiful bridge between quantum field theories and this. So please don't feel shy when you were doing condensed matter physics experiments that somebody talks about Chern-Simons theory. It's nothing but some way of rephrasing something that's chiral, handed thing. So there are ways of understanding it. So don't be scared by field theories and field theories. So, for example, so how am I doing with respect to time?
You're doing fine, you have time.
Sorry?
You're doing fine, you have time, yes?
How much time do I have?
Well, about 20 minutes.
20 minutes, good. Sorry. See, I'm trying to go back in time sometimes, but then I don't succeed. Okay, very good. So, beautiful notions like, decoherence, Hilbert's decoherence-free Hilbert space corners, breakdown of eigenstate thermalization, quantum scars, Hilbert space fragment, many things are happening. And K theory, M theory, thanks to Ashok Sen, ADS-CFT correspondence, thanks to Maldacena, category theory, many things are happening. Many of them look mathematical, very mathematical of course, but then I'm told that please don't be afraid of mathematics. But I'm afraid of mathematics on my own, but still they say it. So I pretend as if I am not afraid of mathematics. Yeah, it's amazing. And also the web of science that quantum matter physics has done is wonderful actually. See, if you take superpluvium 3, it was predicted by Phil Anderson and others, and experimentally it was observed and they got Nobel Prize and so on. Now, suddenly they found out there are glitches in neutron stars. That is, neutron star, if you look at the period, there is a shift in the period of rotating neutron stars. So it was Anderson, Pines and Palmer and others tried to explain it as the surface containing superfluid helium 3, superfluid neutron superfluid, paired neutron superfluid. And that is so suddenly whatever we know reached new stars. So the new stars are going. In fact, Sony was very much interested in this quantum Hall-like phenomena in these things and so on. And then again look at it. People are trying to understand mercury superconductivity. There was some inconsistency, gauge invariance problem. Anderson looked at it very carefully. Said if you want to do a gauge invariance formalism, you will have to what is the Goldstone mode of a superconducting order parameter will become a plasmon. So that's the famous Anderson's mechanism of plasmon mass generation. That was noticed by Higgs and others, and they converted it into a Higgs theory of elementary particles. So suddenly you jumped from dirty condensed matter to profound nuclear matter, elementary particle, mass of quarks, electrons, and so on. Similarly, black hole, who would have thought the quantum spin liquid will have something to do with black hole physics? According to SVK model and according to Kitaev, in fact, it exemplifies some of the phenomena that happens in black hole physics. So I will not go into the detail, but I am just encouraging young people to look at it. So basically what happens, Hilbert space is Hilbert space that we are used to in quantum matter is incomprehensibly vast. So we are all voyagers in Hilbert space. Often we get lost. We say it's my territory and it's your territory and so on. Like Columbus, instead of going to India, he landed up in America and then changed. That's what we do. I want to go to a Fermi liquid. I sail in a Fermi Sea, I end up in a Majorana Fermi Sea, and so on. Okay, this again I like this. See, it's often said that more than the sum of the parts. Complexity and emergence we talk about in physics, in quantum matter particularly, A plus A. So let me take these two set of concentric circles. You all see they are beautiful. Put them together. Some people say it looks like a butterfly or some like a insect in the water. Then it looks something similar. What do you see? It's a cat. You can even make it Mu. So look at it. The circles on their own did not do anything, but put them together, you have emergent things. This is a picture I took of something being dried in our house. You see beautiful Mayer pattern. I have seen this with my mother's sari when she dries it, so that's why I took this picture. And I asked my grandson to help me. He helped me with this 8 years ago. Mayer pattern in some new dhoti. Okay. Now, again, physics is full of emergence, and A plus A is not 2A. For example, there was a beautiful discussion between apparently Niels Bohr and Ernst Mayr. Ernst Mayr was a very famous evolutionary biologist. So he boasted to Niels Bohr about emergence in biology. Everything you don't know, you know the atoms and molecules, you don't know what's up, why this flower is beautiful and why biology is happening and so on. Then Niels Bohr said, see, Mr. Mayer, physics is even more than that. Physics is full of emergence. You asked him how. Take water molecule like H2O. So I understand what a hydrogen atom is. Ernst Mayr agreed, you understand what a hydrogen atom is, because Niels Bohr understood it very well. Then I put two hydrogen atoms, I get hydrogen molecule. Then I put a water, then I get a water molecule. Then put clusters of water molecule, like 3 of them, there is a cooperative tunneling of protons. And many things happen, quantum phenomena, and also fluid mechanics emerge, Navier-Stokes equation, turbulence. Turbulence is something we don't understand at all. Mathematics of turbulence involves quantum field theory, descriptions. So If you look at ice in its phase diagram, it has about 12 phases, the biological world. So, if you know all about oxygen or hydrogen, doesn't mean that you know about water or biological water. So that's the meaning of emergence. So this was beautifully put by Phil Anderson when he was being ridiculed by high energy physics friends that you guys are doing what is called squalid state physics, dirty physics. What is important is standard model, most basic thing. Then he, as a reaction, he sort of said, more is different, a very famous article. I encourage young people to download it, it's freely available. Broken symmetry and the nature of hierarchical. He says, at each level of complexity, entirely new properties appear. That's a thing that we see in current. So you are in a garden in which everything is different and everything is beautiful. Broken symmetry. So he says everything, the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. This is something like this. You give me Schrodinger equation of a droplet of water. So many Avogadro number of atoms are there. I cannot solve them. It's not useful. But then at every level I can produce new phenomena like proton hydrogen bonding and new things and cooperative phenomena and so on. So construction hypothesis breaks down when confronted with the twin difficulties of scale and complexity. To each level of complexity, entirely new properties appear. Psychology is not applied biology, nor is biology applied chemistry. We can see that the whole becomes not merely more, but very different from the sum of its. But this is a beautiful paper by Phil Anderson. Now, I am saying that more is even more different in the quantum world. For example, this is a paper I wrote, Graphene and its fascinating attributes. There is a book edited by Professor Rao and collaborators. And I contributed an article about quantum complexity in graphene. If you take carbon, you know about two forms of carbon, namely diamond and graphite. They are the two manifestly beautiful forms. Diamond is supposed to be a metastable state because graphite is the lowest energy state. But then, it takes billions of years to transform one to the other, doesn't matter. But then if you take carbon atom and start building things, you can go to the diamond world, which is a rich man's world, so let's avoid it. Then go to graphene. You can have sp2 plus sp3, then you can have a world of carbon nanotube fluorines. And if you just stick to graphene sheet alone, you have sigma bond, pi bond, honeycomb lattices, two-dimensional pi system, Dirac cones. And, all these things happen wherever I have marked. That means, for example, if you look at it carefully, use this 2 Dirac cone and put a magnetic impurity, you get 2-channel Kondo effect, Majorana phenomenon. This is a work that I did with our friend. He's one of our first organizers. What's his name? The Krishna Sen, sorry. Please don't tell him that. I forgot. Krishna Sen Gupta. So 2-channel Kondo effect. And then spin 1 collective mode with Akbar Jafari. And doped graphene, room temperature, possibly room temperature with Vijay Shenoy from IISc Bangalore. And many things are possible. See, nobody could have guessed that this kind of branching will take place. So defects as gauge fields and Lorentz, even one of the work that I am very proud that, I didn't contribute much to this work, but my colleague R. Shankar is a great guy. When I told him, and Venu Lucas was a student, he was well-trained high energy physics student. So when I told them, they solved it next day using some time Lorentz boost and so on. What they said was, if you have a graphene and apply crossed electric and magnetic field, and then solve the problem, it looks like Lorentz boosting. So there is a Kaluza-Klein collapse and various things happen. So you can talk about time dilation, analog of time dilation and space dilation and so on, and vacuum collapse. So many things happen just from simple graphene emergence. This is the couple, great couple who is no more unfortunately. TVR gave me this picture of Phil Anderson and his wife Joyce. They are a wonderful couple on Wormhose. And this Anderson Joyce garden, I went in 2009, I took this. Let me tell a story about this, very important for young people to do this. Many people talk about Anderson's success and so on, so hard work, which is true, but I partly attributed to his gardening. Now when he was at Bell Labs, at some point, he decided to buy a 5-acre of land about 10 miles away from Princeton in a place called Hopewell. I forget the name. And start gardening and removing rubbish. So he and his wife used to work. His wife used to work for 5 hours every day. He used to work for 3 hours every day before he comes to the office. There was no gardener employed. So that I say is the secret of Anderson's success, gardening. So he was a field experimentalist and he did field theory, quantum field theory and so on. So I encourage people, if you have opportunity to do gardening, please do it. Don't feel shy. Because manual labor is something very important and respectable. And these days many people do this actually. I know some family friends who are successful software engineers in Chennai. They gave up everything and bought about 20 acres of dry land in the southern part of Tamil Nadu. Now they are doing farming and they are very happy couple. You know about Abdus Salam and the great... I am showing this because Abdus Salam indirectly contributed to the development of condensed matter physics in many ways. I will not go into the detail. This is Atish Dabolkar, the current director. And the story is fascinating. Again, it's very important to develop good friendship with people whenever you meet in conferences like this. The story is, Abdus Salam was a professor in Imperial College. He was very fond of third world countries. He wanted science to permeate there because we were falling behind in modern science very much. So he was talking with his friend Paolo Budinich. Paolo, I want to do something about it. Paolo said, don't worry, Abdus. I have a friend I am from Trieste. I have a friend who is mayor, is my good friend. So I will get any amount of land you like. So that's how he got this beautiful piece of land near Adriatico Palace. And that's the beginning of the friendship, and it transformed the way physics is done. Because many people do not recognize the important role that ICT played in the beginning of theoretical physics development in India, China. At the beginning, now we are independent, but at the beginning it played very important role. In fact, I have a talk about it. You can do a Google search and find Abdus Salam and ICT. I gave a memorial talk in Jamia Millah. There I describe that. So my message to young people who are part of this garden is, please develop new friendship, and if he may have a rich billionaire uncle, get some money from him for doing science. Because in fact, these days I am very excited about this possibility of private funding for basic science in India. Because for example, people talked about this quantum mission and so on. I am very sorry to say that we are spending nearly about 5,000 crores for quantum mission. 5,000 is less than $1 billion. You take Urbana-Champaign alone, the budget is about, for quantum science is $2 billion. So we as a nation cannot boast of spending too much money. We are not spending money, but at the same time, we should approach private donor. Lots of potential is there. So I encourage people like you, if you belong to a family with a billionaire, please spend some money on basic science and so on. And I should also tell about Lodha. How many of you heard about Lodha Builders recently? Amazing film, Lodha Foundation. So Mr. Lodha, I was there in the inaugural function of this Lodha Foundation for Theoretical Physics, Lodha Institute for Theoretical Physics. So he has given $300 million, which is 2,000 crores, to pure mathematics and theoretical physics. So I am remainder of Michael Lazaridis at Perimeter Institute, who has given $400 million to theoretical physics, open-ended. He says, please don't worry about application. He always gives this example of Maxwell. Maxwell, when he discovered Maxwell's equation, it was a way of unifying things using theory that he knew at that time, using calculus. There was Gauss's law, Biot-Savart law, Ampere's law. They were all separate law. He brought them together, and to his great surprise, he found a wave equation which described waves traveling with speed which is coincident with the velocity of light, well known at that time, or known approximately. So he was shocked. Faraday was shocked. He didn't believe Maxwell's result. Then it took time, 20 years down the line, Hertz discovered it. 20 years later, J.C. Bose and Marconi started wireless communication. The world is different now. So Michael Lazaridis and others say that it's very important to do open-ended basic science, blue sky research. Just don't worry about it. Don't ask. Somebody may ask for quantum computer tomorrow or day after tomorrow. You say that I can deliver it today evening. Please don't tell lies like that. Think about doing basic science carefully. You will do wonders. Okay, this is Phil Anderson. He's a very passionate person. He enjoys talking to young people. Also very important to tell about, I tell people, please attend schools and so on. School, summer school, whenever possible, please go there. Because you'll, by the way, my first visit to Delhi was not long back, 1969. I was in my second MSc. There was a notice saying that there is a summer school on mathematical physics in Delhi University. So I asked my professor, he said, please apply. I got it. So I come to Delhi and land up in Goyar Hall or some hall somewhere. It was a peak summer, and I was fascinated because the lectures were given by very good people. The same physics that I learned in Madurai is taught in Delhi also. To me, I'm coming from Madurai. Physics is physics, in Madurai it should be different. I didn't believe in universality at that time. So, and I developed friendships. Even now, the people that whom I met are good friends now. So it's very important to attend schools and so on, develop friendship. Also, I remember another phenomena. It was one of these hottest, the temperature rose up to 47 Celsius, dry. I could not even sleep in the night. The next day there was this Andi, beautiful storm from the desert, and it cooled down. There was a beautiful rain. So I remember that. So that's the beginning of my association with Delhi, and I'm continuing, and I was visiting my friend Vikram Soni regularly and so on. So Muthu Kumar, this is, he became later a collaborator of Phil Anderson, and in his own words, he's like a Besso. And then Manas Sardar, Indrani Bose, and Ullad. Okay, now we see success. What's the secret of the success? Is something that because when we do physics, we compartmentalize with somebody who does experiments alone, or somebody who does theory alone, or mathematics alone. But there is some grand unification possible. What there was a meeting, Anderson's 50 years of contribution. So his friends and collaborators spoke. I was also asked to speak, so I was very proud and said that, began my talk and told the audience I will begin my technical talk. I will give a model for secret of Anderson's success. He was sitting in the front. He said, what this chap is telling about my success. He looked at me and he raised an eyebrow. Then I said, keep looking at experimental results and contemplate, you will discover the right model. That everybody agrees, because what does Anderson do? He looks at body of experimental results, susceptibility and so on. Then it gives him some concepts, new concepts, which comes as I will give you examples in detail. This model that is his brainchild, but however Anderson cannot solve the model. Even finding approximate solution becomes challenging and formidable. Sometimes there are too many possible solutions. Hilbert space is too vast. What does Anderson do? This is what I said. So Anderson goes back to experimental results and looks at them again and again. Experimental results suggest and guide him to the right solution, the model he has invented. So then I got a smile from Anderson. Because once he told me about one of his former students who is a Nobel laureate, he said the problem with him is he tries to solve problems using mathematics, not using physics or experiments. So that's the way Anderson. So please don't ignore when you see a body of experiments. Please look at them, contemplate on them, think about them. Very, very important for young people. This is also very important. It's also Anderson's rebel attitude. He joined as a postdoctoral fellow at Bell Labs. Shockley was a terror. He was there. So he gave a problem to Anderson saying that please do some specific calculation for barium titanate, which is a ferroelectric. He said, no, I will not do it. So apparently he got very angry. He was protected by Charlie Kittle and Conyers Herring. Please leave that young man alone. And what did Anderson do? He spent the next 2 years knowing about general theories of things, and then he came up with this idea of soft mode theory of ferroelectric. That's a famous theory of Anderson. So it's important to do things abstract rather than focusing on one thing abstract. When particularly a body of results are available, you have the pleasure of having many, many things, and deep insights can be gotten by a careful analysis. Okay. So just to give you how this kind of attitude can do, this is what I call as Anderson model or theories, and I call it as Anderson Tower. These are all some of the Anderson's contributions which I have found out. See, it's a very fascinating. When he joined Harvard, he didn't join Schwinger or others who are fancy theoretical physicists, field theory background. He joined Van Vleck, who was a very humble theorist, doing phenomenological theory. He was interacting with Bloomberg on nuclear magnetic resonance issues and so on. So Anderson was told that there is a line-shaped phenomena, pressure broadening and emotional narrowing phenomena that you see, you don't have a theory. So Anderson worked hard and did a theory which became famous, first work of Anderson, theory of spectral line shapes. Kubo later independently discovered, it's called Kubo-Anderson formula or something. Then spontaneous symmetry breaking, Anderson Tower. Where we talk about charge frustration, spin frustration. In fact, if you take manganite, magnetite, Fe3O4, around 200 Kelvin there is a transition from the charges get reorganized, Fe3, FeO4, Fe2 plus Fe3 plus, there is a reorganization, that's called Virvi transition. Anderson gave a theory of called charge ice. In fact, it was Sriram Sastry and Artremer and other, they introduced the notion of spin ice, wrote a beautiful model, thank you. And that's a famous thing. And then soft mode theory, BCA, and it's very fascinating. The stories are following. When BCS theory came, half the world did not believe it because there was a problem with gauge invariance and it was very mysterious and so on. So Van Vleck and Pauli, Pauli, famous Pauli, Wolfgang Pauli were friends. So one day Pauli met Van Vleck and asked what's happening. He says there is this excitement about BCS theory. So what do you think? I think I have no idea about it. Then he asked him, what does your young Phil Anderson think about it? He says it's right. Then it must be right. That was Pauli's statement. So that's a kind of honor that he had. So what did he do? Anderson, he didn't worry about his own idea. So he tried to rewrite BCS theory in a way that others can understand in terms of pseudo-spin model and so on. It's a big story how it led to Josephson effect eventually. I will not go into the details. So that is responsible for Anderson's work is responsible for Anderson-Higgs model and Josephson phenomena and so on. Similarly, many things you can see. It's a picture, beautiful picture that I think I thought it was done by somebody whom I knew. And when I wrote him, he said, I'm not such a great artist. So I don't know who he is, but this is the artist who has written this beautiful. So Anderson says, as a gardener, what shall I plant next? You can see motional narrowing and various things, spin glass and various things. One can give a lecture on. In fact, I took this picture from Phil Anderson's office. There was a framed picture. I took a picture, and later when Anderson passed away, I could not get the origin of this. Who did it? I thought he told me somebody. I forget the name, but he said no. I am not a good artist. Then it was in Aspen, 1987. By the way, I wish we have Aspen in India. No, we have India is a beautiful country. We have Kashmir, we have IIT Mandi, and so on. So we should have physics center all over the country. Some should be in the hills, somewhere in the ocean, and so on. We have Andaman, Nicobar, and Lakshadweep Islands. So why don't you people, thinking about having some schools like Aspen. Aspen is a great place. Even the Colorado Mountains is on the top of the hill. The summer it's a green and beautiful gardens. There is music festival going on. So in the music in the background you can sit and discuss physics. So at that time I was visiting Aspen. So then I got excited by I saw some bees and running around. Then I drew this postcard to Phil Anderson and sent it to him. And I saw these flowers. To me at that time I was so fascinated with lanthanum copper oxide and oxygen p orbital. They look like p orbital and d square x square minus dx square minus y square orbitals and so on. And later somebody said it looks like C60 molecule, but that's a afterthought. Then graphite is a home. So when I sent this I thought I would just sketch it and send it to Anderson. Anderson got excited by it. He said that, see, the title says Anderson Bhaskaran is a Tamil, because RVBs becomes RBB. So that is his conclusion. Then he says he made some comment about. So I'm just, at least he was happy at that time. Okay, now if you look at the notions that are beautiful now, we have notion of electrons and hole, composite fermion, Majorana fermion, plasmon, many things, Laplacian quasi-particle. Now many fascinating things are happening with respect to this anionic quasi-particles and topological quantum computations and so on. Okay, this is Chanchal Majumdar. Again, it's very important to have good friends, critical friends. So, and make use of that. See, it's very fascinating if you look at the history of Anderson, Nobel Prize winning Anderson model. There was a beautiful theorem due to Majumdar and Cohn, saying that if you take a Fermi C and put an impurity, and if the impurity potential says the bound state formation is analytic, there is no non-analyticity. So they used various things, but then they did not do it correctly according to Anderson. So Anderson was worried about various things. So this is the thing. Say a soluble model, they solve the model, but there's nothing dramatic is going on. we'd say we're standing on the shoulder of friends. What did Anderson do? He said that yes, if you do it carefully, at low energies, this impurity creates soft excitation. They make it orthogonal. That's the famous Anderson's orthogonality heteroscopy that began. So thanks to the insight from Majumdar and Walter Cohn, he built on it. So please make use of friends and build things on it. And then Majumdar-Ghosh model. And by the way, I do not know how many of you remember Klaus Schluter was a great computational biologist. Also, he started a strongly correlated system. He gave this idea of quantum entanglement playing a role in bird sensing magnetic fields and so on. So one day we had a breakfast together. He told me that, Bhaskaran, I use computation as a computer microscope because these days you cannot do many experiments accurately, whereas you can do simulations and so on. So use your results to build models rather than just as the end result. So this I also always tell people, wealth of the data they generate gives us rare and precious wisdom what goes on inside. So use those wisdom to build mathematical. That was his suggestion. So I also tell people who do lots of numerical simulations on, please use them to build models. It's very important. See, when Majumdar and Ghosh wrote the model, did they were excited experiments? No. They did detailed numerical analysis of finite spin system with computing interaction, and they found this. So it agrees with what Schluter has said. Use computer microscope and build a model, and that became a famous model. In fact, my first exposure, I think this will be told, I will finish it very soon, to Majumdar-Ghosh model was not long, by 1970. So I joined physics department in November 1970 or so. Then it so happens the DA symposium is that year, is in Madurai American College, my alma mater. So I was so happy I went there. I listened to 2 talks. One talk was T.V. Ramakrishnan giving a talk about spin fluctuations. So I didn't know anything about spin, but then I learned about spin fluctuation at that time. Beautiful talk by T.V. Ramakrishnan. Second talk was by Pasupati, J. Pasupati, high energy physicist. He was a good friend of Majumdar and Ghosh in TAFR. So he said, you guys have written down, you say that you suspect it's a ground state, but I give you exact proof. So you read out the Majumdar-Ghosh Hamilton in a way where the ground state becomes exact. So it was 10 minutes, so that I understood it. So that was my first exposure to that. So please attend conferences and listen to talks. Then later in 73, there was a summer school at IIC Bangalore, TAFR summer school. I had wonderful teachers and so on, like, I'm finishing it. Sriram Shastri was sitting next to me and he was explaining to me the work that he did on Heisenberg chain. So that was my first exposure to RBB theory at that time. Anyway, so I can keep on going. Let me complete my talk. Okay, just the last thing I want to say. See, we have been living in the comfort zone of equilibrium statistical mechanics. But if you go slightly away from equilibrium, the wonderful things happening. So whole world to be exposed. I did some work recently, so I have no time to explain it. Similarly, biology. You think biology is always classical because beyond chemical bonding and hydrogen bonding, nothing much happens. That's not true. Quantum biology is becoming in a big way. So please listen to it. So let me complete my talk with that general random walk. Thank you very much. Thanks once again for this opportunity to be part of this garden at this time. Sorry if I overshoot my time.
No, it was wonderful and you did not overshoot time.
Thank you.
Let us thank Professor Bhaskaran once again for Professor Bhaskaran, if you are okay, can we...
Any number of questions, yeah.
So he is ever enthusiastic about discussing and talking. So there is one question.
Thank you, Professor Bhaskaran, for this nice talk.
Yeah.
So actually, since the talk was about mostly like philosophy and story, I would like to have like some kind of philosophy. So,
Philosophy, my God.
Yeah.
Tough for me.
Because the thing is that as an experienced subject matter theoretical physicist, I'm an experimentalist, purely experimentalist. As a theoretical subject matter physicist experience, how do you see the predictive power of condensed matter theory?
Oh, yeah, the predictive power comes from people like Anderson through models. So you look at a body of experiments and make measurements, and then keep looking at it, contemplate, then you conceptualize certain things. Sharp concepts, they are not approximate, sharp concepts. Then you make a caricature. It's like a caricature, but caricatures are extremely helpful. They can change the world. They can some caricature can appear in a newspaper and can change the voting pattern and so on. So condensed matter physics is predictive comes from many of these models, caricatures. For example, if you look at modern condensed matter, like this twisted bilayer graphene, it's a caricature of reality in terms of this kind of Meyer patterns, but reality is much more complex than that. So I agree that condensed matter physics is predictive often through the caricature or the models. If I may,
I understand the point.
Yeah.
So I think still we are hopeful. That means because as you already showed in this nice paper, this mode is different. The idea of Anderson came from the idea of or disregarding the ideas of reductionism, right?
correct, exactly,
From
yeah.
that actually evolved this mode.
Correct, exactly, yeah.
Then later on it came basically the quantum protector modeling concepts of quantum protector around 1998 and 2000s. Yeah. So that's the reason I wanted to see
Yeah.
because as an experimentalist, of course, it is very difficult for us often to see what is going to happen. Yeah.
Even as a theorist, it's very difficult for us to have. Yeah,
Okay, thank you very much.
yeah.
Any other question? General query from students?
We'd love to have some questions from students.
Yeah.
You can say, sir, I didn't understand you at all.
At least one question from the students, if not more. Oh, there is one. Yes. Please speak loudly because.
Or you come forward and
Yeah, or you can come to me.
shout. Please come forward. Or I can pass on the microscope. Not microscope, microphone. Shout from there. Majumdar Ghosh model. No, please. I have a.
Nazdeek aa jaiye, koi na. Please come. Sorry for not having the mic. Please come. Bataiye.
No, shout. Majumdar. Or, Deshi, why don't you shout whatever he says?
You have the stage for you. Come on, come there. Yes.
I want to know about the excitation.
Good. So, it's a very good question. One of the first works was by Sriram Sastry about excitations of Majumdar Ghosh model. Because it's an ordered balanced bond solid, there are two degenerate states. So, one of the excitations will be a domain wall. So, it will be like spin-ons or soliton domain wall. And in fact, Sastry did some analytic approximate work and found the spectrum which is gapped and so on. We can chat about it. And also another thing about these models is, Shastri-Sutherland model, when we are old friends, so I was making jokes at him. Nada, what have you written? This is what is going to happen. Then he laughed at me and we were making the topic change. Then later, I found there are beautiful compounds which are almost 100% agreeing with the Shastri-Sutherland model. Not only that, beyond the model there are new features that are, they only wrote down the model in the ground state. Fantastic magnetization plateau, connection to fractional quantum, and many things are happening. So models are like spaceships. They take you to new worlds.
Thank you. Yeah. Maybe just one last question in the interest of time, and then we will. Yeah.
So you mentioned that as we increase the complexity of the model,
Yeah.
as you include more and more interactions, you get to discover new and new physics.
No, I didn't say that. So, for example, you draw the picture of Mahatma Gandhi. It's a caricature, right? You can immediately make it more complicated than it's. So what I'm saying is, look at body of experimental results and draw a new caricature for them. For example, Fermi liquid there will be one caricature, for non-Fermi liquid there will be another caricature, Hubbard model, Heisenberg model, and so on. Maybe I didn't understand what one.
So if you are making a model,
Yeah.
like where do you stop? Like how much?
What is the minimal exactly? So that's a question about. I asked artists. See, somebody there is no blackboard. Mahatma Gandhi just two stroke can tell you it's a Mahatma Gandhi. How do you say that? Or there is a famous cartoonist. In fact, his 100th anniversary was celebrated last year. You know Abu? He was a famous artist. He has a caricature of some famous Congress leaders, and also Reagan. He is well-known artist, Abu Abraham. So his son-in-law is a theoretical physicist, Vikram Vyas. Anyway, so it's like caricature. How do you? So you have different caricature. Don't make it too real. Also, models have like caricature. They can capture the essence of the thing. Don't use it for high energy. So whenever in fact, very often it's said that Anderson we used TJ model for Q-plate superconductor. He says it's valid only at optimal doping. If you go to low energy doping, then you things that you've thrown away, electron phonon coupling, randomness, everything comes into play. So then there are metallurgical complications in his words. So we should know where to stop using the model. We should be humble enough. We shouldn't overuse it. Like this is what Tony Leggett often says. You guys use model, but be careful.
So I think with that, let me close this talk and thank Professor Bhaskaran for a wonderful walk through this garden of quantum matter. Of course, there is so much to explore, and we have next 4 days to explore that. Now I just see that Arindam Ghosh, a colleague, has arrived. So this is the right time to invite him on dais. Here he is. And please present a token of memento to Professor Bhaskaran. Thank you. It's too yeah. So, Arindam, hold on. Because you were on the list to speak, why don't you just spend next 2 minutes?
2 minutes
to say something.
I think Bhaskaran should have the last word. He had. I have the last word. Oh, you have the last word. Fine. The organizer has the last word, so and no one can refute that. First of all, I'm really sorry for the delay and the partly caused by the aircraft. For the first time, the aircraft hit the ground and then took off and delayed me 15 minutes. But at that point of time, I was thinking that it will be difficult. My attending QMAT is uncertain, not just this one, but probably the subsequent ones as well. But it's good that I'm here, and it's a fantastic job that that's done by Satyabrata and the Brijesh and other local organizing committee. Quantum condensed matter is thriving and is becoming bigger. That's partly reason what, everything that I would have said, essentially Bhaskaran said it wonderfully. So I don't think I can add anything more to that. It's becoming a technology, and quantum technology is essentially what quantum condensed matter physics is, except for the fact that you start applying it for chemistry, biology, and computer science and various others. So now it's a good time to expand, and this is exactly what this conference has done. I think we should be having more and more people. I feel, again, precisely what Bhaskaran has said. One of the key areas where quantum condensed matter should expand to is to reach out to other areas which we do not usually consider as quantum condensed matter. And with new technologies coming up and quantum condensed matter becoming closer to the society, I think it's time to expand. It's time to expand beyond just one area, focused area, and start thinking about a holistic scientific view, whether it is going towards cosmology or high energy physics, understanding concepts there with condensed matter analogs, or even reaching out to interdisciplinary soft matter physics, chemistry, biology. How do we encompass larger areas? And condensed matter physics is probably at the place where it can lead the goal, lead the science, which will be a scientific endeavor that will be sustainable. And it will no longer become too focused that tomorrow you lose relevance. And that's where I think we are we need to strive for. And in that sense, I feel that this conference is absolutely the right first step. This endeavor of the organizers here is essentially to forget about this alternating years and let everybody speak, let everybody express their views, and find ways to do that is, I think, the first leadership that the condensed matter physics is going to take. Thank you very much.
Thank you very much, Arindam. Thank you. Yeah, we can do this. Thank you very much. So I think we are at the very end of this program. And now I invite my colleague and convener of the conference, Satyavrat, to make concluding remarks. Satyavrat?
There for the next program.
Yes, please come.
So, welcome to JNU. Mano buddhi ankara chittani nahang na cha shrutra jivve na cha grhana netre na cha vyoma bhume na tejo na vayu chidananda rupa shivoham shivoham. This is new JNU. I can boldly say in JNU, the man is a social animal, man is a political animal. There is something in us that compels to form societies, that compels to, it's not just utility, it's not just self-defense that motivates us, something in us, and it's very common in animal kingdom. I mean, bees form social network, swans form social network. There is a tendency to have prides to schools, right? So this grouping is very much part of, our social upbringing. And I'm very glad that this conference is nucleating some kind of condensed matter community. It's not that it was not there, it was there. And as rightly said by Pratap, alternate years we used to meet, and it's very happy that almost 600 participants, and very happy for the students. 350 students, all of them are staying in IIT Delhi hostels, all in final year, mostly in senior PhD students, postdocs, and they're going to listen to 224 talks, and of very high quality. We have all been part of conferences. For the students, it's an exceptional chance to expose yourself to the best that is happening. So I'm very happy about it. About JNU, we are in the newspaper most of the time, for the right reason. But in defense of JNU, I always quote Bernard Shaw, where he says, a reasonable man adapts himself to the society. An unreasonable man persists in trying till the society adopts him. Therefore, all progress depends on the unreasonable man. So that quantum of unreasonableness is very essential for to discover new things, and whatever is happening in JNU is part of that. Particularly humanities-centric university like ours, you have to contest, you have to put a question mark, and that role of JNU is a positive, one has to see it in a positive light, particularly students' training part. I'm not trying to justify a lot of politics in the campus, but unreasonableness is part of JNU culture, and that's, I think, very positive thing. About my school, School of Physical Sciences, it's a kind of physics, chemistry, maths together under one umbrella, a very new experiment, I think, started by Professor Susanda Dattagupta and Professor Ram Ramaswamy. You know how people fight for 1 square foot extra lab space. And here physicists, chemists, and mathematicians together under one roof. And we have survived, and truly an interdisciplinary program. Chemistry students can take physics courses, physics students can take mathematics courses. That's the aspiration, that something new is being tried. And how far we are successful, time will tell. But I think there are lots of positive even about our school. The next tough part. So we are going to have you must have seen the timetable for the next 4 days, jam-packed, right? So the first Vinati hai sare session chair ko, please insist, more than what Brijesh could do today, that if it is 25 minutes plus 5, please ensure that. And there are 5 parallel sessions, something shifts, the next session is delayed, there is no such chance. So please, session chairs, Vinati hai ki, be whatever way you can dance in front of the speaker. 25 plus 5 minutes means 25 plus 5 minutes, right? Your people have to close in that, because we have actually in every session, there are 5 very good talks by faculty members and 3 by postdocs and students. And so I would insist that if we put it in time, then the PhD students and postdocs would get, those are the least priority, those are the highest priority. But unless we really are very careful about timing, then at the end you would find that there are no audience for the postdoc. So the first requirement is to do that. The conference starts every day sharp at 9 a.m. And those students who are staying at IIT Delhi, right, There are green buses running all the time. Don't go by auto or Ola or anything. Please, and breakfast, lunch, dinner is included in IIT Delhi, right? And so you have your breakfast, and please somehow reach here by 8:45. And as I told you, I mean, if you want to go to Agra or Rishikesh, you're most welcome. I mean, will not make any arrangement of waking you up and giving you a bus and bringing you here. That's not going to happen. It's your option. But if you really want to learn from the masters, this is a golden opportunity. Please be here by 8:45 a.m. All 4 days, there are fantastic review talks and, of course, the parallel sessions. So don't miss out on this opportunity. And evenings were kept absolutely free. Just across the mall, you have just across the JNU Road, you have the Delhi's biggest mall. And interesting thing is that their chappal is sold for 3 lakhs rupees. And that's not surprising. People like you and me, complete contrast to JNU economic theories, go and buy that. And so that's what is happening. You should have a view of Imperio or Ambience is middle class, but Imperio you should go in properly dressed, otherwise they will not allow you to get in. There's lots of things happening. Houskers village is very good. There's a lake there. Lots of eateries inside JNU. Ganga Dhaba is very famous. Mughal Darbar is there, very, very Mughlai cuisine. So look at the campus. 1,400 acres of land surrounded by realty, not buildings, but reality. I mean, inside this is completely different kind of reality that is there. So enjoy JNU. Most welcome. We'll have a high tea, quote unquote high tea now. Tomorrow we meet sharp at 8:45. I think Arindam is the review talk. And so my request to all the students would be, please make arrangements so that you have your breakfast at IIT and please be here on time. Thank you very much. Yes, you want to say something? Two more points. Please come in. Yeah.
One is about the student registration. It is still on because they need batches for going.
Yes, student registration is still on. I mean, it will be there tomorrow also. The advantage is that if you have that badge, you can come to the VC gate. Then the walk is really beautiful. It's hardly 1 kilometer walk. Even autos would be allowed. If you have that badge, so which you can take it. So now I think we can open it again, registration, right? So students, if that helps you. Otherwise tomorrow 8 o'clock again the registration desk would be open.
I think they need it for hostel to show something in the
hostel.
Yeah, somebody was telling me that the
no hostel is
not required.
No hostel is not required.
The second point is about talks. The morning. So maybe I can just say.
Yes, please.
So just a request to sort of manage the whole jam-packed program. We request all the speakers for the morning session to kindly send their PDFs to the email of the QMET conference so that they can all be pre-uploaded on the computer, preferably PDF file because that is not system dependent so much. And then the chair can easily manage and everybody changes the talk quickly soon after. So this is a humble request. Please send your talks anytime before the morning session. And those who will be giving talks in the afternoon session are expected to send their talks anytime in the morning. And this will repeat every day so that the sessions run in cohesion and without losing time.
There are a slightly difference of opinion. Not many people want to really share their slides. Yeah. So there is always a half an hour break, tea break. We don't want people to bring their own laptop, but if you have a memory stick, we can load it here. If you are willing to share it with PDF, that is fine. But there are 25 talks every session. Organizing the session by session. Where you will send that. So if you want to do it, it's fine. But half an hour break that we have, we will load all these talks. We would not encourage you to bring your own laptop and connect an Apple and that. All. Yeah, so that's fine. Yes, please.
Please make PDF.
Some connectivity issues will be addressed, but during the tea break, please try that thing, sir. Yeah.
But this is the point that instead of everybody connecting.
Please have a PDF backup.
Please make a PDF and send
backup.
Or through the stick, because it will really save the time. Otherwise, changing itself takes. So
sure.
If every talk delays by 2 minutes, 20 talks means 40 minutes. We will be.
And there are 3 or 4 vehicles that we have. In case of emergency, I'll give you the phone number. You give a call, and but students it will be difficult. But faculty members who are staying in different guest houses, we can just, morning hours, if there is a rush, we can do it. But it is easier that you just walk in and every 5 minutes there is a bus that will come to the auditorium directly. Okay. Thank you very much. Most welcome. We meet at the high tea. Thank you.